Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Annelin Sindane. The lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center and broadcast by Palama Research and Development. Today's lesson is differential calculus. We are going to look at the applications of calculus in sketching and interpreting cubic functions. At the end of the lesson, you should be able to determine roots of a cubic polynomial using the factor theorem. You should be able to sketch cubic polynomial functions from a given equation using differential calculus. You should be able to interpret cubic functions. You may refer to the CAPS document as well as to the examination guidelines as outlined there. Now, for us to be able to do this, we are continuing from the previous lessons. We did functional notation when we're doing functions. We did factorization of our cubic polynomials using the factor theorem as well as the remainder theorem. This knowledge is very important in us understanding and being able to tackle questions that involve cubic polynomials. We should be able to factorize cubic polynomials using long division, synthetic division, as well as inspection. We should be able to sketch functions. We have done this on our previous lessons. We should be able to understand the meaning of a derivative and apply it correctly in sketching and interpreting our cubic functions. I will go straight to the factor theorem. Given a polynomial f of x, if x minus c is a factor, then it follows that f of c will be equal to 0. Then it is given that x minus c is going to be a factor to that polynomial, and f of c is a 0, meaning c is a root or a solution to that equation. Now, the remainder theorem says if f of c is equal to r, then it follows that the remainder when f of x, which is our function, is divided by x minus c, will be given by that particular value that you get when you substitute your c. That's the remainder theorem. So for the factor theorem, our remainder is 0. So it is a perfect factor. Then we move on to the next part. We can use the following methods. I know we have been taught long division, synthetic division, as well as inspection. Learners, the choice is yours. The examiner will not prescribe which method to use, but you should be able to know at least one of the 3 given methods for you to be able to tackle questions that involve cubic polynomials. Now, I'll go straight to the steps of sketching a cubic polynomial. 1. Normally, we are given the function as f of x is equal to ax cubed plus bx squared plus cx plus d. We know that a determines the shape of our cubic polynomial. If our a is positive or greater than 0, we know that we will have an increasing function like that. So the shape, the function will increase up to the maximum turning point, then it will decrease, then it will increase again if our a is positive. That determines the shape of our cubic function. If a is less than 0, meaning if our a is negative, we will have a decreasing function. So our function will decrease up to the minimum turning point. It will then increase, then decrease again. So there are two areas or regions where the function is decreasing. Hence, the first shape we say if a is positive, our cubic function is an increasing one. If our a is negative, our cubic function is a decreasing function. Now, to get the intercepts, we do it the same way we do for our normal functions. X-intercept as well as the y-intercept. For the y-intercept, we substitute our x as 0. And if we are given the function as above, it would mean that the y-intercept will be 0 and d. That will give us our y-intercept there. And our x-intercept, we know that we need to find the first factor using the factor theorem. Once we get the first factor, we are able to factorize the cubic polynomial either using long division, inspection, or synthetic division, whichever we are comfortable with. So once we get one factor, we can use those, and then we are able to factorize the cubic polynomial. Or if we can't factorize, you will have one factor, which is perfect. Then you can use the quadratic formula to simplify the other to help us get the other two roots so that we are able to sketch our function. Next step, we need to get the x values at the turning point, and we are going to use calculus in that we know that at a turning point the gradient is 0. Hence, we will do the first derivative, equate it to 0, then solve for x. The values of x that we get are the x values at the turning point. We will take those x values and we substitute them back into the original function that we are dealing with to help us get the corresponding y values at the turning points. Now, we have looked at the y values at the turning points, and then we've got another special point that we need when we are sketching our cubic function, which is our point of inflection. Point of inflection is where our concavity changes. If our function is increasing, for example, we get a point somewhere in the middle here where our function changes from being concave down, it then becomes concave up. If we are having a decreasing function at the point of inflection, it means our function will change from being concave up and it becomes concave down. It is a very important point that we must know, and we should be able to use calculus to determine that point, or we can use the other methods that we have learned from functions to get that point of inflection. Now, I would want us to sketch the graph of f of x is given by x cubed minus x squared minus 8x plus 12. I know you have already done this at school. If I could just give you 3 minutes to help you get the first factor, and then you use it to factorize that polynomial. Just 3 minutes let's try that one and see how far we can go. Right, I hope you have had a good time solving this. Now, the first thing, if we check, the coefficient of x cubed there is 1. So it means our a is 1, meaning a is greater than 0. So the shape of our graph, we are able to determine it before we do the sketch. Then the next thing is to get our x-intercepts. So to get our x-intercepts, we know that our f of x is equal to 0 because our y values are 0 when we get our x-intercepts. So we are going to solve the equation x cubed minus x squared minus 8x plus 12 is equal to 0. Now, we then use the factor theorem to help us get the first factor. Normally, I encourage people to start using the smaller ones. You can use -1, 1, -2, and 2. Then, if it does not give us, then you try 3, 4 to help us get the first factor. Others are able to use the calculator. It's still fine, but it's important to know the factor theorem. Now, we try another factor. I tried 2. And when you substitute 2 in place of x, you will find out that it gives 0. We conclude using the factor theorem that our x minus 2 is a factor. After this, we are able to do the factorization either using synthetic division or inspection as well as long division. Now, I have already done the simplification. You will get x minus 2 into x squared plus x minus 6. When we do the factorization, I used inspection just to illustrate. I am solving the equation x minus 2 into, for me to get the first term x cubed, I will have x squared here. I can put bx there, minus 6, because negative 2 times negative 6 will give me the last term. So to get this middle term, it's easy. I know it's easy to get the first factor and the first term as well as the last term. So those are the ones we use mostly to do the factorization. When I move from here, I am able to now get my x. I'll take the terms that will have a variable x squared. So it means if I multiply this x by that b, I will get bx squared. If I multiply negative 2 by x squared, I will get negative 2x squared. And comparing this to the original function, I'm able to see that the coefficient of x squared on the original function is negative 1. I then get the value of b as negative 1. When negative 2 goes across the equal sign, you will get negative 1 plus 2, and this will give my b as 1. That's how I got my middle term there, b. So I've managed to factorize using inspection. The choice is yours, learners, which method you are comfortable with. In the exam, it will not be prescribed for you. So from there, I've done the factorization, x minus 2 into x squared plus x minus 6. I need to factorize the second bracket, and I'm able to do the factorization, and then I will be able to get my x-intercepts as, if I check, 2, 0 appears twice, and the other x-intercept will be negative 3 and 0. I then move on to get my stationary points. We are aware that our y-intercept will be given by 0 and 12. We evaluate f of 0, and we know that we'll get 12, so meaning this will give us our y-intercept. To get the stationary points, which are our turning points, we need them. We are going to use calculus. At a turning point, we know that the gradient is 0 because that's an equation of a horizontal line. It will be given by y equals. The gradient is 0, so we are going to differentiate. And then from rules of differentiation, we'll get 3x squared minus 2x minus 8. That's what we get when we do the first derivative. Then we know that the first derivative gives us the gradient function. So the gradient function, meaning our gradient is equal to 0 at the turning point, we'll substitute 0 in place of the first derivative, and we will get 3x squared minus 2x minus 8 is equal to 0. We are able to factorize that. Please practice factorization, but if you can't, you are allowed to use the quadratic formula, and then we'll get our x values at the turning points as 2, and the other x value at the turning point will be negative 4 over 3. Now, for you to get the corresponding y values, you substitute the x values into the original function, and you will get 0 for x equals to 2, I hope you have already realized something, that once you get an x-intercept appearing twice, it means it is both an intercept as well as a turning point from your practice as you answer these questions. So we substitute the other x value, which is -4/3. It will give us our corresponding y value as 500/27. You can use your calculator to change it to decimal. Now, we have our turning points. What are we left with? We need our point of inflection where our concavity changes, so that when we sketch our graph, we are able to know when to change our concavity. Now, our point of inflection, we know that to get that one, the method that you can use using calculus, you can do the second derivative. You get 6x minus 2. We know that at a point of inflection, our second derivative is equal to 0. We substitute in place of f dash dash x, we substitute 0, and then we solve, and we'll get our x as 1/3. From there, the x value that we get, we substitute it back to the original function, and this will give us a value of f of 1/3. So where there is x, we substitute 1/3, and we will get 1/3 and 250/27 as a decimal. That will give us 0.33 and 9.26. Now that we have all this information, we are now able to sketch our function. So we go to our answer book. First, we have our Cartesian plane. I don't have a ruler, so mine it's a bit not straight. We'll have our x, we'll have our y. What is the starting point? Please, a sketch is different from drawing. We show the key features, which are our intercepts, our turning points, as well as the shape. That's all that the examiner will be looking for. We do not have to waste a lot of time measuring. When we are supposed to do a sketch, we show basic features. The first part, we have done our x-intercepts. We got -3. We got 2 and 0 as one of the turning point. We also got -3 and 0. 2 and 0. For our turning points, let's quickly check. What did we get as our turning points? Quickly check our turning points. We got 2 and 0 and -4/3 and 500/27. So let's quickly move, and we are able to sketch our point of inflection. We have it. So let's get the turning points. We got -4/3 and 500/27. The other one, 2 and 0. Then our point of inflection, we got 1/3 and 250/27. Now we come here. Our -3 should be somewhere there. Our -4/3 should be, let me put 1 here. And our -4/3 should be somewhere on the right of this. Let me put it there. We also need 2 and 0. 2 should be somewhere there. We also got 0 and 12. 12 could be somewhere there. And then our turning point, we got negative 4 over 3 and 500 over 27. So quickly, 500 over 27 should give us 18 comma something. So it means our graph, remember our shape, because a is greater than 0, our shape is increasing like that. So our function will increase, passing the x-intercept up to a maximum turning point, then goes through our 0 and 12, and then we have the other turning point there. I will move my 2 that side so that I have a smooth shape. Our point of inflection, we have it as 1 over 3 somewhere there. Our x will be 1 over 3. Now we are able to do the sketch. As you can see, that's a rough one. And then I gave you the sketch. It will be as follows. And we get our marks. Please try to make sure that your curve is smooth, so you are able to show your x-intercept, it's -3 and 0. Your turning point, the maximum turning point becomes -1,33 and 18,52. Our y-intercept, it's 0 and 12. Our point of inflection is 0,33 and 9,26. And the minimum turning point is going to be 2 and 0. That's a sketch of a cubic function, and we should be able to do this one. So this is for the increasing one, our f of x. So when you are answering your question, you just indicate f of x. When we mark, we are going to look at the shape. Is it a smooth curve? Because some of us, when we sketch, we use a ruler, and you'll find someone drawing a graph like that. Please, if you do that, you will not get a mark for the shape, because this is not a cubic function. It's a letter Z that has been drawn there. So please make sure you do a smooth curve. You show the basic features. It must show smooth, maximum turning point, minimum turning point as a curve, not as if you are joining two V's. Now, that's the shape. And for this one, maybe you are able to get 4 marks because you are able to show the coordinates of the turning points, the x-intercepts, the y-intercept, as well as the shape. So you might get 4 marks or so. Now, I would give you some time now to sketch this graph. I'll give you about 5 minutes. You use whatever method of factorization that you are comfortable with, and then you sketch the graph of f of x is given by -x cubed minus 2x squared plus x plus 2. I'll give you 5 minutes. You find the factors and then you sketch the function. 5 minutes. Welcome back. I hope you have had a good time. Now, let's quickly do the sketch. Our a is less than 0 because the coefficient of x cubed is -1. And then from there, we know that the shape of our function will be a decreasing function. Now, to get the y-intercept, our x is equal to 0. So we are able to get our y-intercept as 0 and 2. To get the x-intercept, we know that our f of x is equal to 0. So we are solving that equation. Now, from there, you can use the factor theorem. If I check this function, it is easily factorizable, so I can use my knowledge of factorization to factorize this. I will demonstrate quickly. I have negative x cubed minus 2x squared plus x plus 2 equal to 0. I'm able to see that x squared is a factor of those terms. I'll factor out x squared. Let me factor out negative x squared. I will remain with x plus 2 plus that one. I can put 1 outside and I'll remain with x plus 2. So I can use factorization by grouping to do this question. It's not always that you have to use synthetic division, long division, or inspection. Please check the type of question that you are dealing with and work accordingly. So from there, I'm able to see that I'll have x plus 2 and I'll have 1 minus x squared equals 0. Then I'm able to factorize this, x plus 2. 1 minus x squared is a difference of 2 squares. It will be 1 minus x, and the other factor will be 1 plus x equals 0. And then from there, I'm able to get my x-intercepts. X will be equal to -2, or x will be equal to -1, or x will be equal to 1. Now, let's use the factor theorem. If you substitute 1 there, you are able to see that it gives us 0. Our f of 1 is 0, meaning x minus 1 is a factor. Then you can use your long division, synthetic division. As I have demonstrated, you can use factorization by grouping. It gives us the correct answer. We do the factorization and we get our x values as the ones that I have shown you before. Our x-intercepts are those. We have 3 of them. Please be careful as well. They can ask you of roots. Remember, what you get as your x-intercepts becomes the root of the equation that you are solving. We move on now. We have found the y-intercept, it's 0 and 2. We have found our x-intercept. We now need the turning points, which are also known as stationary points. So we differentiate first derivative at a turning point, gradient is 0, we equate to 0, we now know that part. Now, if you check, our first derivative is -3x squared minus 4x plus 1. We cannot easily factorize that. There are no factors, so you are allowed to use the quadratic formula or the method of completing the square, whichever you are comfortable with. But I know the method of completing the square is not a favorite for most of us, so we can use the quadratic formula. And please check the formula on your formula page. Some make mistakes when they substitute into the quadratic formula. There's no mark for writing the quadratic formula. There's a mark for substitution into the quadratic formula as it is given in the formula page. So I will substitute and I will get my x values as -1,55, and the other x value at the turning point will be 0,22. From there, I substitute those x values at the turning points to my original function, I will get negative 1,55 and negative 0,63. I will also have 0,22 as well as 2,11. So because my function is decreasing, it will have a minimum first, increase, then have a maximum. So the shape will be like that. Now, to sketch the graph, I also need my point of inflection, and I will derive the function for the second time, and I'll get negative 6x minus 4. We still remember the rules of differentiation. It is the exponent multiplied by the coefficient. So 2 times negative 3 will give us negative 6. 2 minus 1 will give us 1. So x to the power 1 is x minus 4. And we equate the second derivative to 0. And that will give our x at a point of inflection as negative. Let's substitute. It will give us 20 over 27, which is 0,74. So the coordinates of the point of inflection, I've abbreviated the point of inflection. So now we have all the information. We've got our x-intercept, we've got our turning points, we've got our point of inflection, we've got our y-intercept. Now we can sketch the graph. Now I've already sketched it for you, and our graph should look something like that. You can mark yourself. You will get your x-intercepts, the 3 of them, your y-intercept 0 and 2, the turning points, and then the other mark goes for the shape. You will get your 4 marks there for sketching. I hope it was an easy one. Let's move on to the next part. Let us look at interpreting our cubic functions. Now, the meaning of the first derivative. The first derivative, remember, we used average gradient to get the first derivative. And we said it is the gradient at a point. In this case, the first derivative gives us the gradient function of any point along the curve that we are dealing with. It also gives us the instantaneous rate of change anywhere along that particular curve. So we should be able to use the first derivative correctly. Now, I will just look at the concavity part that I was talking about, where we are saying, if you look at a cubic function, it's a connection of 2 parabolas, one concave up, the other concave down, depending on whether it is an increasing or a decreasing function. Now, we're able to see that if you are to substitute into the first derivative function, which is our f dash of x, you'd substitute a value of x on the left of the x value at the turning point. You will find out that if it's a maximum turning point, the gradient will be positive. It then becomes 0 at the turning point. Then when you substitute any other x value on the right of the x value at the turning point, the gradient will be negative. So we are saying our function is going to increase up to the turning point, then it will start to decrease like that. If it is a local minimum, if it's a minimum turning point, meaning our curve is concave up or at the point where we have our turning point, our function will decrease, meaning if you substitute an x value on the left, you'll get a negative gradient. If you substitute our x value at the turning point, we'll get our 0. then we will also get a positive on the right. So meaning it will decrease, turning point, then it increases again. That's the interpretation. Now, this first derivative is very important because in some questions we are given information about the first derivative and the second derivative. The question will ask us to sketch the original graph, as you will see on the activities that we are going to do later on. Now, we have seen a maximum at point A. You will see it will increase. At the turning point, it is both increasing and decreasing. Then it starts to decrease again. That's a maximum turning point. And then we will also have our minimum turning point. As I've illustrated, it will decrease. We have our turning point, then it is increasing. So it is difficult for us to tell whether at the turning point what is actually happening. So we can just say it is both increasing and decreasing depending on the shape that we are dealing with. Now, also for some cubic functions, you will find out that there is no maximum or local minimum. We only have one point, and the point of inflection is both the turning point as well as the point of inflection. And the shape of the graph would look something like that at point A. And f of x at x is equal to A, we say it is increasing. We also have that where we have our decreasing function. The point of inflection is also a point, it's also a turning point, and we will have the shape of our cubic function being like that. It is both, it is decreasing at the point of inflection, and the shape will be like that. And then if we want to summarize the types of our cubic functions, as indicated, if our a is greater than 0, our cubic function takes that shape. We can have it when it has two stationary points. We can have where we have the stationary point as well as the point of inflection being at one point. And then we only have another one where we only have a point of inflection. The shape will be like that. If our a is less than 0, our decreasing functions, we are going to have the two scenarios that we are having here. Now, I want us to look at the relationship between our f of x, which is the original function, as well as the first derivative function f dash of x, as well as the second derivative function, so that we are able to see the relationship amongst the given functions. Now, I hope I will bring in the question that we just did for our f of x is equal to x cubed, the one that we sketched first as our first graph. Now, you will realize that our function was increasing. I will indicate those regions. Our point of inflection, our other minimum turning point. I want us to look at the interpretation and how we can use this to solve cubic functions. You are able to see that for the first function, we had our maximum turning point at -4/3 and 500/27. I want us to dwell more on the x values, and which is what the questions normally asks us to understand and to know the relationship. If you check, our x value at the turning point was -1,33. If you look at the black graph, is the graph of f of x. The green graph is the graph of f dash of x, the graph of the first derivative function that I have sketched. And the purple graph is the graph for the second derivative function. You are able to see the relationship there. The lines that I've drawn is to show the connection. You are able to see that where our f of x is increasing, it increases up to the turning point, which is x is equal to negative 1,33. You are able to see that our f dash of x, the first derivative function, you will find out that it is positive where f of x is increasing. So there is a relationship there. I want us also to look at our point of inflection, in which case it is our x value there, it's 1/3. You will find out that where our f of x is decreasing between the two turning points, you will find out that the first derivative function, our f dash of x, it will be less than 0. You are able to connect. So between the maximum turning point and the minimum turning point, our f dash of x is negative or is less than 0, and our f of x is decreasing in that given region. So that takes the x values at the turning points, the relationship. So you are able also to see that our other turning point was x is equal to 2. You will realize that where our f of x, the black graph, is increasing, you are able to see that our first derivative function, which is our f dash of x, is greater than 0. It's on the positive side of the y values. That's the relationship that we have. Also, I want us to look at now the point of inflection where concavity changes. We said concavity changes at x is equal to 0,33. If you check, our concavity changes from being concave down, our graph becomes concave up at 0,33. You are able to see that where our function f of x is concave down, our function f dash of x is decreasing up to that axis of symmetry, which is the turning point. So where our f of x is concave down, f dash of x is decreasing. From the point of inflection where f of x is now concave up, you will realize that our f dash of x, let me use the negative sign to show that it is decreasing there. And then from here, from the turning point of the parabola, which is our f dash of x function, the gradient is positive. You will realize that our concavity, our f of x is now concave up like that. So that is the relationship that we have between our f of x and our f dash of x. I've also indicated using our second derivative function. Where our second derivative function is positive, are you able to see that? Also, you are able to see that that is where concavity changes. The graph of f of x, look at our x value there, it's 0,33, isn't it? Concavity changes at 0,33. If you check, the graph is now concave up. Look at the graph of the purple graph. From 0,33 up to positive infinity, you will find out that our f dash dash of x is always greater than 0. It's on the positive side of our y values. And before, for our x, less than 0.33, our f of x is concave down. And our f dash dash of x, you'll find it's on the negative side of our y values. So our f dash dash of x is less than 0. So that is the relationship that we have there. So this information is very important because examiners sometimes will give us these questions and will ask us to either sketch or to interpret a point of inflection or interpret a turning point when they've given you a sketch of the first derivative or the second derivative function. It is important to understand these concepts. Now, let us look at the comparison using a decreasing function. There is the decreasing function. I will use our graph 2 that I asked you to sketch. I've already sketched it. We got our x-intercepts like that. That's a decreasing function. Let's look at this relationship. You are able to see that the x value at the turning point is also the x-intercept. The point of inflection, our x value at the point of inflection becomes the x value at the turning point of the first derivative function. And the other stationary point, it's also the x-intercept. So there is a relationship. To prove this, I have sketched the two graphs on the same set of axes, as well as I have also sketched the second derivative function. If you compare, on the previous one, f of x was increasing, and the second derivative function was also increasing. It had a positive gradient. And if you look at this one, the first derivative, the original function is decreasing. The second derivative function, the purple graph, is also decreasing. It has a negative gradient. So there is a relationship between our original function, first derivative function, and second derivative function. If you want to check, this function is decreasing, our a is negative. The first derivative function will take the form f dash of x is given by negative 3ax squared plus 2bx plus c. Already the coefficient of x squared is negative 3a, meaning that parabola will be concave down. And you are able to see the relationship there. I will also indicate using the x at the turning point. I'll also indicate using the point of inflection as well as the maximum turning point for that function. We are able to do the same deductions that we did for the previous graph. You will find out that now the opposite occurs. Where our f of x is decreasing, you will find out that our f dash of x is less than 0. You are able to see that our f of x is decreasing up to the turning point, negative, negative, up to the turning point. Look at our green graph from negative 1,55 to negative infinity. The graph is below the x-axis. It is negative. Hence, we say f dash of x is less than 0. Now, you will also realize that where our f of x is increasing between the two turning points, check our green graph. It is on the positive side of our y values. So we say our f dash of x is greater than 0, where f of x is increasing. Then, where our f of x is decreasing again, you are able to deduct the same. Our f dash of x is less than 0. Now, let's look at the point of inflection. Concavity changes. This is a decreasing function. It will be concave up, then concave down. Our point of inflection, we got it as negative 0.67 or negative 2 over 3. You are able to see that this function f dash of x increases. I'll use a positive sign. I know it's now ugly there. Up to the turning point, then it starts to decrease again. Again, let's make the deductions. Where f dash of x is decreasing, you will find out that the second derivative function is less than 0. Our f dash dash of x is less than 0. Where our f dash of x is increasing, our f dash dash of x is greater than 0. That is the relationship that we have. Now, our point of inflection, so also concavity changes there. You are able to see that where f dash dash of x is greater than 0, our graph is concave up. Where our f dash dash of x is less than 0, our graph is going to be concave down. I hope you are able to follow this. If not, just take a picture of this, and when you are relaxed, you are going to go over it again, because it is important to get the relationship between the original function, the first derivative function, as well as the second derivative function. Now, we are moving on now so that we are able to answer exam type questions. And I'm going to give you 8 minutes to attempt that question. We are going to mark it together after 8 minutes. Let's attempt that question. Welcome back. I hope we have had a good time doing the solution to this question. 17 marks in the bag. Let's look at the first question. We are given a sketch. The most important thing before you start writing, understand the information that you are given. Normally, when you are given a sketch of a function, in most cases, you are supposed to come up with the equation. When you are given the equation, in most cases, you are supposed to do the sketch. We should be careful about that. Now, the graph is f of x is given as x cubed plus bx squared plus cx plus d. So the first thing that you notice, the value of a is given. The shape of the graph is given. So coefficient of x cubed there is 1. The solutions to the equation are of f of x is equal to 0 are negative 2, 1, and 4. Those are our x-intercepts. So it means that one, it's negative 3. That one, it's 1. That one is going to be, it's negative 2, 1, and 4. So those are our x-intercepts. So you can write 4, 0, 1 and 0, negative 2 and 0. Those are our x-intercepts. Now, what comes into your mind? You know that we have got 3 forms. So it means to get our f of x, it will take the form a, but we know the value of a is 1. So it will be x minus x1, x minus x2, x minus x3. We use the coordinate form of the equation. We substitute our x-intercept, so our f of x becomes x minus negative 2, that becomes plus 2, x minus 1, and x minus 4. We then expand and we'll get x plus 2 into, we will get x squared minus 4x minus x, that gives us negative 5x. Negative 1 times negative 4, we get positive 4. We then distribute that, we will get x cubed minus 5x squared plus 4x plus 2x squared minus 10x plus 8. We then collect like terms. We get x cubed. Negative 5x squared plus 2x squared will give us negative 3x squared. 4x minus 10x will give us negative 6x plus 8. So that is the equation. Therefore, you look at the equation, our b is negative 3. Our c is equal to negative 6. And our d is equal to 8. Then we get our 5 marks there. So substitution, simplification, and then the values of a, of our b, c, and d. We get the answer there. We move on to 9.2. Please read the question. Calculate, underline the keyword, the x coordinate of b. It didn't say the coordinates of b. You are only calculating the x coordinate there. So our f of x, we already have it. We got x cubed minus 3x squared minus 6x plus 8. Turning point, we want f dash of x, and that will give us 3x squared minus 6x minus 6. We need to solve for x, so we know that our first derivative will be equal to 0. 3x squared minus 6x minus 6 equals 0. X squared minus 2x minus 2 is equal to 0. Can we factorize this? Not really. So we use the quadratic formula. X is equal to negative b. Our b is negative 2 plus minus the square root of negative 2 squared minus 4. Our a is 1 and our c is negative 2. All this over 2 times 1. And if I look at this, b should be the turning point that has a negative x value. I will then punch this into my calculator. I think we should get our x as negative 0.73 or our x as, quickly on our calculators, negative, let's punch in negative 2. I'll use the minus square root brackets negative 2 squared minus 4 1 negative 2 over 2 times 1. Yes, I'll get 1 minus root 3. The other one will be 1 plus root 3, of which I need the one with a negative sign. I'll change the sign here to a plus, and this gives us 1 plus root 3, and that is x equal to 2.73. It's not applicable for b, ne? So the x value at b will be equal to negative 0.73. We get our full marks for doing that. We move on to the next question. Determine the equation of the tangent to the graph of f at x is equal to negative 1. Equation of a tangent, we know that our f of x is given by x plus 2, x minus 1, x minus 4. So we want to find out f of, at our x value is negative 1. So we need to get the corresponding y value at the point of contact. So we evaluate f of negative 1 and we'll get negative 1 plus 2, negative 1 minus 2, negative 1 minus 4. So let's quickly get the answer there. We'll get a 1, negative 3 times negative 5. What do we get as the coordinates of that point? Let's quickly get them. So we get our f of negative 1 as let's quickly confirm. We'll get negative 1 plus 2, negative 1, oh, that's minus 1 there. So we will get negative 2 times negative 5, and this will give us positive 10. So it means the coordinates will be -1 and 10. Now, our first derivative, our f dash of x, we calculated it earlier. We got 3x squared minus, we got our 6x minus 6. So we evaluate f dash of -1. We'll get 3 times -1 squared minus 6 times -1 minus 6. What do we get as the gradient? So we should be able to get our gradient there as 3. We'll have 3 plus 6, we get 9, minus 6, we get 3. So our equation will be y is equal to 3x plus c, using the equation of a straight line. And then we are going to substitute the coordinates -1 and 10 to give us the equation. We'll get 10 is equal to 3, -1 plus c, and we'll get our c as 13. Therefore, the equation of the tangent will be given by y is equal to 3x plus 13. You are able to see that -1 is just before the turning point. Therefore, our tangent should be something like that. It should be an increasing one. The gradient is positive, and our y-intercept is on the positive side. Please check if your answer makes sense whenever you are answering these questions. We move on to the next question. Let's move on to the next question. In your answer book, sketch the graph of the second derivative function, clearly indicating the x-intercept as well as the y-intercept. So our first derivative, we got 3x squared minus 6x minus 6. Our second derivative will be 6x minus 6. Now, this is our function that we are dealing with. To get the x-intercept, we know that to get the y-intercept, we're going to say, remember, this is not the derivative. We are dealing with the function as it is. F dash dash of 0 will give us -6. So we will have our y-intercept as 0 and -6. Our x-intercept, we are solving 6x minus 6 is equal to 0. And we are going to get our x as 1. So meaning our x-intercept will be 1 and 0. We are... my space there is affected. Let me quickly go back. Now, so my x-intercept will be that one. I'll use the question to help me sketch the graph quickly. So I see that my y-intercept, it's somewhere down there. I'll say this is my -6. And somewhere here, I will have my -1. And then my graph is a are you able to see that something is not right there? Because my gradient is positive, my graph is correct. So I have to take it to the other side. My 1 and 0 is there. Here I have -6, 0 and -6. So if I draw it the way I've drawn it, you'll realize that the graph doesn't make sense because this one is a decreasing function. Yet the graph that you should be sketching should have a positive gradient. So this one is not the correct graph. So the correct graph should have a positive gradient like that. So this is the graph of f dash dash of x. 1 and 0 as our x-intercept, 0 and -6 as our y-intercept. please check that your answer always makes sense before you write it down. We move on now to the next question. So the previous question has helped you to get your point of inflection, which is x is equal to 1. And we know that concavity changes at a point of inflection. If you check this graph up to there, it is concave down and then it is concave up. So we solved f dash dash of x. We got 6x minus 6. So we are saying f dash dash of x is greater than 0 when our graph is concave up, and you can solve and get 6x minus 6 is greater than 0. 6x is greater than 6. Our x is greater than 1. But from the previous question, where you sketched the graph of the first derivative, of the second derivative, you were able to see that we had a scenario like this, where here we had our 1 and 0, and we said at x is equal to 1, our f dash dash of x, because it's greater than 0, the graph of f of x is concave up. So you are able to see that this is the point of inflection, and you can easily write the answer as x is greater than 1, or x is an element from 1 to positive infinity. So that is the region where our graph is concave up. Now, you may kindly take question 8, a picture of question 8. You will answer it later on because I want us to move on to the next question, as we will not have enough time to go through the questions. But I want us to look at an interpretation question after this. Have 1 minute to take a picture of this question. It also involves a lot of interpretation there. Right, I hope you have managed to take the picture there. It's an interesting question, 15 marks there. Now, to just talk about it, you are given the equation of the function. You are given information about the first derivative. Now, what do you realize? You are able to deduce that x from the information given, f dash of 1 equal to f dash of 3 equals 0. You are able to see that x equals to 1 or x equals to 3. These are our turning points because the first derivative is equal to 0. You are given information about the turning points there, and you are given the coordinates of one of the turning points as 1, because f of 1 means our x is 1 and our y value is 4. That's a turning point. And looking at the function, you are able to see that this is an increasing function. And also, when you solve that equation, you'll be able to see that one of the x-intercepts is also a turning point, and that will be at x is equal to 3. Then you are able to work out that question. So you are able to expand, find the first derivative, find the second derivative, equate it to 0. Then you are able to show that the point of inflection is x is equal to 2. But we'll do this question at a later stage. I want us to move now to the following question. Now, in an exam, you'll be given information like that homework question where you are just given information about f dash of x, f dash of negative, f dash of 3, being like that. I want us to quickly do this in 2 minutes. Use the above information to draw a sketch of f. It's not g there, it should be f because we are dealing with f of x. I'll give you 2 minutes to just try and do the sketch of that graph. Sorry, 1 minute, 1 minute, because time is not on our side. I want you to interpret that information and you sketch the graph. 1 minute. Welcome back. I hope you managed to deal with these 4 marks. Now, they've given us information about the first derivative function, x less than 0. This is what I was explaining, the relationship between our original function, first derivative, and the second derivative. So what can we deduce? If f dash of x is greater than 0, we know that for x less than negative 3 or x greater than 3, we are able to deduce that f of x is increasing. And then we are able to see that between negative 3 and 3, we are able to deduce that f of x, because f dash is less, we are able to deduce that f of x is decreasing. Then we are able to notice that x equal to negative 3 or x equals to 3, these are our turning points. We are also able to see that our 0 and f of 0, it's on the positive, so it means our y-intercept must be on the positive. So using this information, I'm able to quickly sketch the graph. I will have my y-intercept, my y-axis, my x-axis. I realized that I have negative 3. I also have 3 here as a turning point, and I know that my y-intercept must be positive. So I'm able to see that because from the information given, it's an increasing function, so my function will increase up to the turning point. It will decrease between the two values, and then it will increase. So because they have not told us about the turning point of that other point, I'm able to get my marks here. This will be negative 3 when I'm sketching, and f of negative 3 as my maximum turning point. This is my 0 and f of 0. That's my y-intercept. And my other turning point, it will be 3 and f of 3. So you are able to get your 4 marks by showing that your y-intercept is on the positive side. Your turning points at x is equal to -3 and the other turning point at x is equal to 3, and then you get the mark also for the turning points as well as the other mark goes for the shape. You have your 4 marks there, and that will be the solution for that question. 4 marks is a lot. 1% out of 300. It determines whether you are changing a level or not. Now, here's another interesting one. Please take a picture of it. I had planned it for homework. You are going to look at it and then you are able to do the sketch of that graph. So just take a picture because time is no longer on our side, and you will do it later on. These are interesting interpretation questions. Now, yes, I hope you've managed to take the picture of the question. So, in summary, we should be able to apply the method that we have discussed on using the factor theorem to find one of the factors. You factorize using synthetic division, long division, or inspection, and then you are able to use calculus to find the turning points, to find the points of inflection, and thereafter you are able to sketch the function. The relationship will come as we move along. You should be able to understand the relationship between the original function, the first derivative function, and the second derivative function using calculus. We should be able to interpret the cubic functions correctly in relation to the derivatives. And we should also be able to interpret functions and other function-related questions using the graphical approach that we learned the last time. And we also use the function notation. Thank you very much for participating, and please continue to study. And COVID is still with us, though not that much, but let's always protect ourselves. So we will see you next time. Goodbye.